Imagine standing under a clear night sky, looking up at the stars that dot the inky blackness above. Each pinpoint of light represents a sun, perhaps with its own system of planets, moons, and asteroids. Our own solar system formed approximately 4.6 billion years ago, emerging from a swirling cloud of gas and dust that collapsed under its own gravity. For decades, scientists believed that everything in our solar system, from the hydrogen in the sun to the carbon in your body, originated within this primordial cloud. But what if some of the building blocks of our world are actually older than the solar system itself? In 2019, Dr. Wendy Goodwin and her team at the University of Chicago made a remarkable discovery that challenged our understanding of cosmic chemistry. Using the Robert C. Byrd Greenbank telescope in West Virginia, they detected a complex organic molecule called benzonitrile in the Taurus molecular cloud, a stellar nursery about 430 light-years from Earth. When we first saw the spectroscopic signature, I did not believe it, Dr. Goodwin recounted. We analyzed the data again and again. There was no mistake, we were seeing a complex carbon-based molecule in interstellar space. This discovery was significant because benzonitrile is a precursor to polycyclic aromatic hydrocarbons, PAHs, a class of organic compounds made up of multiple aromatic rings. PAHs are among the most complex molecules found in space and are thought to be important building blocks for life. But the true revelation came in 2022, when astrochemist Dr. Barbara Collins from the Max Planck Institute for Extraterrestrial Physics announced an even more astonishing find. Using the James Webb Space Telescope, her team identified a specific PAH called pyrene in an ancient meteorite that had crashed in Australia decades earlier. Through advanced radioisotope dating, they determined that some of the pyrene molecules were approximately 7 billion years old, predating our solar system by over 2 billion years. These molecules are time capsules, Dr. Collins explained during a press conference at the American Astronomical Society meeting in January 2023. They were born in the explosion of a star that lived and died long before our sun began to shine. They traveled through the void of space for billions of years before becoming part of the molecular cloud that eventually collapsed to form our solar system. To understand the significance of this discovery, we need to journey back to the beginning, not of our solar system, but of the universe itself. Approximately 13.8 billion years ago, the Big Bang created a universe consisting almost entirely of hydrogen and helium, with trace amounts of lithium. All other elements, carbon, oxygen, nitrogen, silicon, iron, everything else in the periodic table, did not exist yet. These heavier elements could only be created through nuclear fusion in the hearts of stars. The first generation of stars, forming about 100 million years after the Big Bang, were massive, burning hot and dying young in spectacular supernova explosions. These cosmic detonations scattered newly forged elements across space, enriching the interstellar medium. Dr. James White, an astrophysicist at the California Institute of Technology who was not involved in the research, explains, when a star explodes, it releases elements forged in its core into space. These elements can then come together to form molecules in the cold vacuum between stars. Before this discovery, we knew that simple molecules like water and carbon monoxide existed in interstellar space, but finding complex organic compounds that predate our solar system changes our understanding of chemical evolution in the cosmos. The pyrene molecules found by Dr. Collins and her team formed in the outflow of a star that lived and died more than 7 billion years ago. After the star exploded, these molecules drifted through interstellar space, eventually becoming incorporated into the molecular cloud that collapsed to form our sun and planets. Dr. Thomas Hanning, director at the Max Planck Institute and co-author of the study, puts it into perspective. About 1/3 of the carbon on Earth, including some of the carbon in our bodies, may have been produced in stars that died before the sun was born. We are not just made of stardust, we are made of ancient stardust. To confirm their findings, Dr. Collins and her team used a technique called isotope analysis. Chemical elements come in different isotopes, variations with different numbers of neutrons. The ratio of these isotopes can serve as a kind of cosmic clock, allowing scientists to determine when the elements were created. The pyrene molecule showed an isotopic signature consistent with formation in a stellar environment approximately 7 billion years ago. Furthermore, these molecules were found in the core of the meteorite, protected from contamination and alteration since the early days of our solar system. These molecules are perfectly preserved specimens, said Dr. Collins. They were incorporated into the solid material that formed the meteorite about 4.5 billion years ago, and they have remained unchanged ever since. But how did these ancient organic molecules survive for so long? The interstellar medium is a harsh environment, filled with cosmic rays and ultraviolet radiation that can break down complex molecules. The answer lies in the protective power of cosmic dust. Tiny grains of silicate and carbon serve as shields, absorbing harmful radiation that would otherwise destroy delicate organic molecules. These dust grains also act as cosmic chemistry labs, providing surfaces where atoms can meet and react to form increasingly complex compounds. Dr. Miguel Gonzalez, an astrochemist at the European Southern Observatory, explains, in the cold of interstellar space, about -260 degrees Celsius, atoms and simple molecules can stick to dust grains. There, they can find each other and react, building up complexity over time. Without these dust grains, the chemistry of space would be much simpler. The discovery of these ancient PAHs has profound implications for our understanding of life's origins. PAHs are important precursors to the nucleobases that make up DNA and RNA, the information-carrying molecules of all known life. It is entirely possible, suggests Dr. Collins, that the very first building blocks of life on Earth, perhaps even some of the molecules in your DNA right now, were created before the solar system existed. This possibility fundamentally changes how we think about the origins of life on Earth. Rather than life arising solely from chemical reactions on the early Earth, the essential ingredients may have been delivered ready-made from interstellar space. The story becomes even more compelling when we consider how these ancient molecules reached Earth. During the early days of our solar system, about 4.5 billion years ago, Earth was bombarded by meteorites, comets, and asteroids, all potential carriers of these presolar organic compounds. Recent studies of comets support this idea. In 2014, the European Space Agency's Rosetta mission detected complex organic molecules on the comet 67P/Churyumov-Gerasimenko. And in 2016, NASA's OSIRIS-RX mission discovered evidence of organic compounds on the asteroid Bennu. Dr. Sarah Mackenzie, a planetary scientist at NASA's Goddard Space Flight Center, puts these findings in context. Comets and asteroids are essentially preserved remnants from the formation of our solar system. They contain materials that have remained largely unchanged for billions of years. The fact that we find complex organic molecules on these bodies suggests they were common in the solar nebula and were likely delivered to the early Earth in great abundance. The implications extend beyond our own planet. If these organic building blocks are common in interstellar space and are routinely incorporated into forming planetary systems, then the chemical foundations for life might be widespread throughout the galaxy. Dr. Elizabeth Tasker, an exoplanet researcher at the Japan Aerospace Exploration Agency, sees this as an encouraging sign for the search for extraterrestrial life. If the precursors to life are ancient and ubiquitous, predating even the birth of stars and planets, then the universe might be more conducive to the development of life than we previously thought. The discovery also changes our understanding of our place in cosmic history. Humans tend to view the universe from an Earth-centered perspective, with events categorized as either occurring before or after our planet formed. But the detection of chemicals older than our solar system reminds us that we are latecomers to an ancient cosmic story. When you hold a meteorite in your hand, you are touching something that is partly made of material from stars that died before our sun was born, says Dr. Collins. It connects you directly to cosmic history that predates our entire solar system. This connection to the distant past raises questions about the future. If molecules can survive for billions of years in the harsh environment of space, what might their ultimate fate be? Some of the pyrene molecules found in the meteorite may eventually become part of living organisms on Earth. Others, contained in asteroids or cometary material ejected from our solar system, might travel onward to other star systems, perhaps one day becoming incorporated into alien biochemistries on distant worlds. The discovery has sparked new research directions across multiple scientific disciplines. Astrochemists are now searching for even more complex presolar molecules. Biologists are investigating how these ancient chemicals might have influenced the development of life on Earth. Astronomers are developing new tools to detect similar compounds in distant star-forming regions. Dr. Robert Garrison, director of the Origins Institute at McMaster University, summarizes the significance. Science often advances by discovering that things are older, larger, or more complex than we previously thought. This finding does all three. It pushes back the timeline for complex organic chemistry, it expands the scale at which we need to consider life's origins, and it reveals that the chemistry relevant to life is more intricate and ancient than we imagined. As our instruments become more sensitive and our understanding of cosmic chemistry deepens, scientists expect to find even more complex presolar molecules. The boundaries between astronomy, chemistry, and biology continue to blur as we recognize that the origins of life's building blocks extend far beyond Earth, beyond our solar system, to ancient stars that lived and died long before our sun began to shine. The next time you look up at the night sky, consider this: you are not just connected to the stars through the elements in your body. Some of the complex molecules that make you who you are might have formed in the aftermath of stellar explosions that occurred billions of years before Earth existed. In a very real sense, you carry within you chemicals that are older than the solar system, time travelers from the distant past that help make life possible in the present. We are not just in the universe, the ancient universe is within us.